Today, we're going to cover a few topics. First off, what do antibodies do? This is going to be something that we will definitely be discussing in Unit 13, which is the immune system. But I want to just kind of tap dance around it without giving away that whole lesson, because we've been talking so much about antibodies. You need to actually learn what it does within your body. So I'm going to give you a real life example, and let's say that it has to do with COVID-19 Delta variant. There's been various mutagenic forms of COVID. There's the Alpha, there's the Beta. Now we have the Delta, we got the Omicron, now we got the Omicron 1A, all this weird stuff. They're all variants. It's just like the flu every year. There's a different flu variant every year. They try to predict what it's going to be, and they make the flu vaccine based off of it. So let's say, hypothetically, one of you gets infected with COVID-19 Delta variant, and you have not been vaccinated, and you have never had COVID before. So let's say this is the actual viral capsule. It's made out of proteins. And on that viral capsule, it has antigens that look like this. Look like a little dog paws or something. Those are antigens. Now, they're definitely not you. I mean, it's a foreign virus, right? Well, let's say this is a respiratory cell. It's been shown that COVID mainly attacks your respiratory system, although it's been shown to attack other organs and tissues too. But let's say this is a respiratory cell, and your cells have receptors on them. Well, I'm sorry to say, those are some receptors. Does it appear as though those antigens on COVID fit into your receptors? Yes. This is how viruses really mess us up. They have the keys to your house. The house is your cells. They know how to get in. You have different types of cells, and different types of cells tend to have different types of receptors. This type of virus will match up with the receptors on your respiratory cells. So basically, COVID matches up with your receptor, and it's like a lock going in a key, or what, a key going into a lock. The virus will then be able to go into your cells, and mainly your nucleus, and replicate itself over and over and over again. Once upon a time, back in 2019, there was one human being with COVID. Now it has affected billions. Some have died, some have recovered, some are long haulers, but this is how every virus works. Not just COVID. This is the flu. This is HPV. This is HIV. This is a lot of different viruses. So if you have never been exposed to a virus and you have never gotten a vaccine, this is probably going to happen. But this is your first exposure, all right? Let's say this is your first exposure. You survive and you recover. Here's what you get out of it: natural immunity. So if you're like me, I got COVID in July. I was vaccinated, but let's just pretend I wasn't. I got COVID-19 Delta variant in July, and let's say in October, I got it again. I was at a party, nobody was wearing masks, there's snot and particles and spit all over the place, and I got it back into my body. What do I have my second exposure that I did not have during my first exposure? I have antibodies. So let's say this is an antibody for COVID-19 Delta variant. Those antibodies are going to latch onto it like gum in your hair. It's just going to cover it. Does COVID-19 currently have any way to get into your cells when it's surrounded by antibodies like this? No, it's going to bounce off your cells like a basketball on the court. It's not going to be able to get in. And you now have a defense for it. This is when I had chickenpox when I was a child. This is what I have now. I have antibodies. You guys have antibodies for a lot of different diseases that you've either had or you've been vaccinated for. Yes, Grace. Somewhere over there. I'm not sure where. You have to look around. They're over by Dylan. Yes.
So if you have the antibodies for it, you still need to get the vaccine.
It's been shown that antibodies may not last forever. Yeah. I'm not a pathologist. I'm not a pharmaceutical technician, but the studies have shown that if you're boosted, or excuse me, if you're vaccinated and you have natural immunity, that's better than just having one versus the other. You should have both. The majority of people that have been hospitalized are unvaccinated. And does the vaccine work once you've gotten it? Not really. I saw a news story where there's a guy in the hospital barely able to breathe, and he says, please give me the vaccine now. And the doctors say it's too late. It's like you don't put on body armor after you've been shot. You don't put your seatbelt on after you've flown through the windshield. It's before. It's a preventative measure. And it takes about 2 weeks for a vaccine to kick in because your body has to learn it. And let me tell you what a vaccine does. So let's erase all this. You don't need to write this down. This is just a little fun fact because we've been hearing about vaccines about every day in our world. What a vaccine does is it doesn't give you the virus, it gives you this. It gives you the antigen. And it allows your immune system to figure it out. And so over the course of like 2 weeks, your body makes antibodies based on an antigen. And so in the future, let's say you actually get the virus with that antigen, you're prepared. That's what it does. But that's an immune system lesson. Let me tell you what actually happens when we are given donor tissue, blood, or otherwise that may or may not have a matching antigen with us. So this is going to lead me to my next topic, transfusions and determining blood type. So Eva, you were the only one that said that you were going to get blood. Here's what they're going to do. I don't know if they still do it today, but when I was in high school, they took my blood, they took my home address, my phone number, my name, all that stuff, birthday, all that stuff. And like a month or so later, there was a little card that came in the mail. And it said, you're HIV negative, which is good to know. Don't have HIV, human immunodeficiency virus. And it said I was like B negative, I think. It said B something. It was a long time ago. Well, how do they figure out your blood type? Here's how they do it. But before we get to that, let's get something understood. Let's say here's Eva. And she's going to be A positive. What antigens does she have on her cells? She has A's. What else does she have? She has Rh factor. Let's say she's driving by and she sees Isabella bleeding on the side of the street. Medical professionals are there, but they need blood. They need blood now, or Isabella's going to die from lack of blood. Eva says, let me help her. I want to help her. I want to help her. She's my friend in anatomy class. Turns out Isabella has B negative blood. What antigens are on her cells? Just B. Would this be a proper match? No. Isabella has B negative blood, which means she would have antibodies for anything that's not her. She would develop anti-A antibodies if exposed to Eva's blood, and she would develop anti-Rh factor antibodies if she was exposed to Eva's blood. So that would be an incompatible match. But what would happen if you actually went ahead and did this? You put a mismatch recipient and donor together. You get a phenomenon known as agglutination. This is what you're going to learn today. Agglutination is basically, this isn't a sciencey term, it's the clumpiness of blood. The blood becomes more viscous, it becomes thicker, it becomes goopy. And if you're a recipient and you're the one that's having this go on in your body, that's not good. So if I could draw Eva's cells again, Here's what would happen if we put Eva's blood into Isabella's body. Just like I showed you how COVID was surrounded by antibodies, that's the same thing that would happen here. And this would cause like a giant traffic jam inside of Isabella's own body. Whenever you guys are going through class change, you're trying to walk out one door and go into main hall, and it's just like a big bottleneck effect. I kind of refer to that as big blood clot. You got a lot of parts, but nothing's moving. That's a blood clot. This is what would happen inside a recipient's body if it wasn't a match. The blood is just going to get really clogged up with blood cells and antibodies, and it's called agglutination. So we need to be sure that we have the proper matches. And so here's what they're going to do with you, Eva, after they take your blood. They're going to have 3 vials. I don't know if they do this on the bus. They probably don't. They have a lab somewhere at the hospital. We're going to have 3 vials here. Vial number 1 is going to be called anti-A serum. We're going to have anti-B serum. And we're going to have anti-RH serum. Sometimes they just call that D, just, I don't know why. But anti-A serum is going to have anti-A antibodies. Anti-B is going to have anti-B antibodies. That means that it goes after antigen B. And then we're going to have anti-RH antibodies. Now, this might take a few times for you guys to really grasp this, and that's totally fine. If you have questions, you need to speak up for yourselves. If you're anything like my other 2 classes today, it takes about 2 or 3 times, and eventually it starts to click. So if you don't get it the first time, don't sweat it. I'm going to go over it several times because it can be a little tricky. Your brain's going to go, wait, huh? Wait, what? Oh, I see. It's going to take a few tries, so bear with me. All right, I'm going to go back to this word called agglutination for a sec. When you look at blood that has experienced agglutination, the blood gets clumpy. It sinks to the bottom of the vial, and it looks just like clotted blood almost. On the other hand, I want you to imagine a glass of water, and I want you to imagine a few drops of red food dye. If I dropped a few drops of red food dye into a glass of water, what will happen to all the water in the glass? It turns red. That's what happens when you have non-agglutination. So when you see a reaction, that means that the antibody and the antigen is a match. It's going to take a few tries for you to get this, but I think you'll eventually get it. So let's say we have Eva's blood, and the technicians or the nurses are going to put a drop of her blood, a few drops, into each of these vials. They need to find out what is her blood type so they know what patient to give it to. So they drop Eva's blood into anti-A serum, and it does this. They drop Eva's blood into the anti-B serum, and it does this. It fills out the whole thing like food coloring. And they drop her blood into the anti-RH, and it does this. So let's take it one at a time. This is agglutination. This means that the anti-A antibodies are reacting with the antigens that are on her cells. The antibodies and the antigens on her cells are a match. So Hannah, if I put Eva's blood into a vial with anti-A antibodies, and the antibodies attacked her cells, what does that say about her? She has the A antigen. So in this one, Eva is positive for A blood. So she's definitely A. She has that. Eva, this is your hypothetical blood. I put your blood into the anti-B serum and there was no reaction. Inside this anti-B serum, there are antibodies that attack the B antigen. They're not attacking anything. Do you have the B antigen? No, you don't. So over here, when it comes to her having B, that's a negative. She doesn't have B. And then Chris, I put her blood into the RH serum and it did react. The antibodies in this vial attacked her cells and it chunkified. Does she have the RH factor? Yes, she does. So she, for RH, she's positive. So what is Eva's blood type given these results? She is A positive. Let's try another one. It's going to take a few tries, I think, for everyone to grasp this. Whoops. Okay. I put in a patient's blood. It agglutinates for A. It agglutinates for B. And it agglutinates for RH. What is their blood type? AB positive. You get this, Isabella?
Yeah.
Let's try another. I drop Noah's blood into all three. No agglutination, no agglutination, no agglutination. No reaction, no immunity reaction. So what is Noah's blood type? O negative. You're getting it. Let's try one more. What time? We got about 6 minutes. Okay. What's that blood type? AB what? AB negative. You have a reaction, there's A. You have a reaction, there's B. There's no reaction there, you don't have RH. You're AB negative. This is how the nurses and the phlebotomists and the other techs that involve blood donations determine a patient's blood type. Here's a bonus question before I put on a phlebotomy video for you. I had a girl last period who says that she plans on getting blood next Wednesday, but she has been denied being allowed to give blood in the past because she has low levels of iron. Why would low levels of iron keep you from donating blood? You might know. Iron allows hemoglobin to carry oxygen. What is the purpose of having red blood cells? Carry oxygen. Basically, your blood is not good at what it is supposed to do. Your blood is supposed to carry O2. When you have low levels of iron, it's not good at carrying O2. So why donate blood if they really can't use it? I mean, here, we'll give you an apple for coming, thank you, but we really can't use your blood. It's not good at what it's supposed to do. Okay, the last thing I want to show you before the last thing I want to define for you before I show you a video is phlebotomy. Eva, you are going to have a phlebotomy procedure next Wednesday. Phlebotomy is simply the taking of blood from the artery of a patient. What do you call a person who performs phlebotomy? A phlebotomist. There'll be several phlebotomists on that bus next week. All right, I want to show you a quick video of phlebotomy. It's way too long to show in class, but if you're watching online, go on YouTube. And where did I put it? Right there. If you type in safe and effective blood draw, that's what we're going to watch right now.